Hello everybody, this is Mr. Strager, once again back with another Big Ideas lesson. Today is the day we are finally out of Unit 2. We are starting Unit 3. One thing that I like about Unit 3 is, in Units 1 and 2, we were entirely focused on just solving problems, figuring out how to solve different equations, figuring out how to solve different inequalities. But once you have the basis for this, it kind of opens up the world to a lot more thinking activities as opposed to formulaic activities. Unit 3 is all about just how you think about different relationships between numbers. Before we get started with our notes on page 61, however, I want to ask you a little bit of something. Does this shape look familiar to you? It might bring back some distant memories from elementary school or something. The shape looks familiar when it comes to mathematics. There's a name that I would like to give this shape. I call this shape the function machine. The function machine. The idea of a function machine is this. You put something in the top. The function machine is then going to change that number somehow, based on a rule. Maybe the rule is to plus 1 or to subtract 7, and then you get an output. So let's do it as an example. Let's say our rule was plus 5. If I put in the number 3, what am I going to get out? Well, 3 goes in. Our rule is plus 5. It'll pop out as 8. So putting in a 3 will give us an 8. What happens if I put in a negative 6? Well, if I put a negative 6 in, we add 5, we'll get out a negative 1. The function machine will take in one input at a time and give you one output. Let's do another example real quick. This time, I'm going to put in, or write down, what's going into the function machine and what's going out of the function machine. You have to try and tell me the rule. So if I put in 0 into the function machine, I get out, well, 0. If I put 3 into the function machine, I get out 6. And if I put in a negative 2, I get out negative 4. Based on this, can you figure out what my rule is? If you want to, pause the video and try and see if you can kind of figure it out. If you guessed that the rule is times 2, you are absolutely correct. Yeah, I'm multiplying everything by 2. 0 times 2 is 0. 3 times 2 is 6. Negative 2 times 2 is negative 4. So, using a rule, we can put things in to figure out what will come out. Or, if you know what goes in and out, you can usually figure out the rule. Although this process is a little bit tricky, and we'll talk about why in a little bit. This is what happens when we have a function machine that works. However, there are some unique cases I want us to take a look at. Just like how we were able to figure out the rule here, I want us to try to figure out the rule for this next one. This one's going to be a little bit trickier. If I plug in the number 1, I get out the number 7. Okay? If I plug in the number 3, I get out the number 7. If I plug in the number negative 12, I get out 7. In this case, what do we think the rule is? Again, this one's going to be a little bit trickier. The rule for this particular function machine is equals 7. It just turns whatever goes in into 7. And that's absolutely allowed. Think of it like a recycling plant. where you can put everything in, anything that you want, and out will come recycled paper. It takes in a whole bunch of things and gives out just one output, recycled paper. That is totally okay for our function machines to do. It can take in a lot of things and give out just one input every time. But let's see what happens in this case. Let's say I have a function machine, and my rule is that I want to, well, we'll keep the rule blank for this part. I want to ask you, let's say I plug in a 0, and I get out a 1. I plug in a 1, I get out a 2. I plug in a 2, I get out a 3. And then let's say that I try plugging in 0 again, just to check. But this time, instead of getting something out that was equal to 1, we got out something like negative 20. Well, hold on a second. The rule seemed clear when we were doing it originally. We were just adding 1. But then when I plugged 0 back in, I got something completely different. This is what we call a broken machine. It's totally broken. Even though it works for some things, for other things, it just totally doesn't work. For instance, when we plugged in 0, we got 2 different results. Imagine if you go to a restaurant, you order the number 0 combo, and the first time you get it, it's a cheeseburger. The second time you get it, it's a pile of radioactive sludge. That is a broken restaurant. A broken machine is one where, when you put in the same input, you get 2 different outputs. In other words, when we plugged in 0, we got 1, but we also got negative 20. The most important thing that we're going to be doing in this unit is not going to be figuring out what the rules are, even though that is something that you can try out. A lot of the rules that we're going to be looking at are actually going to be so complicated, it might be hard to decide. We'll save those for a later date, specifically Algebra 2. This unit is dedicated to picking out when a machine works or when it is a broken machine. As a reminder, machines are fine if you can put something in and get one thing out, like in these two. It's also fine if you can put different things in and get the same output. A machine is broken when, after putting the same thing in twice, you get 2 different results. So let's try some examples real quick. Here's what I'm plugging into my machine. I'm plugging in the numbers 0, 1, 2, 3, and I'm going to plug in a 0 again. If I plug all these into my machine, here's what pops out. The first thing that pops out is a 3. Then we get a negative 2, then a 0, then a 1, then a 3. Obviously, the rule here is going to be really tricky to find, if there is a rule at all. But our goal should be to figure out if this machine is working or if it's broken. Well, let's think about it. When we plugged in a 0, we got a 3. Maybe we can represent this data in another form to make it easier to read. Because as of right now, this is just 2 lists of numbers. We can instead choose to represent data in what we're going to call ordered pairs. And you might have seen something like this before. What we're going to do is, we're going to take our input, so in this case we'll take 0, and put it as the first number in parentheses. To tell us what will come out of the input machine, we're going to use a comma, and then write what comes out. So when 0 is put in, we got out a 3. We write it as this ordered pair, 0, 3. Let's keep writing the ordered pairs. We would get 1, comma, negative 2. We would get 2, comma, 0. This pen is dying, so I'm going to have to change pens, unfortunately. I apologize. When we plugged in a 3, we got out 1. And when we plugged in 0, we got out 3. In any of these cases, were our rules broken? Well, it's tough to say. Originally, you might be tempted to say, oh yeah, the rule broke because we used 0 twice. But look at what happened both times we used 0. The first time we used 0 as an input, we got out 3 as an output. The second time we used 0 as an input, we got out, well, 3 as an output. That means the machine is working just fine. A machine isn't broken, remember, if each input gives us only one specific output. Because 0 will always give us an output of 3, this machine is fine. And there's nothing else that's broken in here. Let's try another one. Let's say I gave you the following information. We're plugging in the numbers 0, 0, 1, 2, and 7. And every time I plug it in, I just get out 2, 2, 2, 2, 2. Uh-oh, do we have a broken function machine? No, because according to our rule up here, you could totally plug in a bunch of different things and get out the same output. That's totally fine. The rule is just that whatever we plug in gets changed into 2. That's just our rule. One more example I want to try out is this. Let's say I have a function machine where I'm plugging in all the numbers 1 through 5. Well, actually, let's do 1 through 3, but I'll plug them in twice. So I'm plugging in 1, 1, 2, 2, 3, 3. And my outputs, I end up getting 0, 0, 4, 5, 6, 7. Is this a broken function machine? This one is a broken function machine, because if I write out the ordered pairs, 1 goes to 0, this one goes to this 0, that's so far working just fine. 2 goes to 4, okay. 2 goes to 5, okay. As soon as we notice that 2 gives us 2 different things, we can already say, okay, our machine is broken. When I plugged in a 2, I'm supposed to get out a 4. Here, I got a 5. But if you wanted to keep continuing, you'd see it gets even worse, because our machine is very broken. If I plug in 3, I get out a 6. If I plug in 3 again, I get out 7. So this is a very broken machine. All right? With that out of the way, I think it's actually time for us to get started on the notes portion of the lesson. So to those following along in your student journal, we are on page 61. On page 61, we have a lot of definitions. And whether you think of it fortunately or unfortunately, these are all actually pretty important. Let's take a look. First things first, we have what is known as a relation. A relation is just something that pairs inputs and outputs. So our function machines really kind of showed different relations. The relation could be, oh, whatever you plug in, you multiply by 2 to get an output. Or the relation could be, whatever you plug in, you get 7. A relation is just a way of describing how inputs turn into outputs. You could think of it sort of as a rule. A function is a little bit different. A function is a type of relation still, so we write out that it is a relation. But the difference is, it pairs each input with exactly one output. In other words, if I plug in a 2, I should get the same thing out every single time. If my function is that we're adding 1 every time we plug something in, if I plug in a 2, I get a 3. If I plug in another 2, I still get 3. If I plug in another 2, I still get 3. A function is a function machine that works. So this is a function machine that works because 0 is paired with 0, meaning every time I put in a 0, no matter what, because the rule stays the same, I'm going to get out a 0. Every time I plug in a 3, you bet I'm going to get a 6. If I plugged in -2 again, I'm going to get another -4. Something that wouldn't count as a function is our broken machines. Anytime we plug in a number twice and get 2 different results, we can immediately say, nope, no longer a function. This will come in handy when we're doing a couple exercises with this. In fact, I want us to do a couple right now. So, here's what I would like you to do. I'd like you to please turn to page 63. And I want you to take a look at problems 1 and 2. Take your time with these and ask yourself, are these functions? In other words, does every number we plug in give us exactly 1 output? Pause the video here and give it a try. Hopefully we had a chance to pause the video and give it a try. If not, no worries, but I know who you are. I'm just messing with you. When we look at problem like number 1, we have to ask ourselves, does every input have exactly 1 output? So, in this case, let's take a look. -2 gives us an output of 4. 0 gives us an output of 5. 1 gives us an output of 4. You might be tempted to say, oh, but I see 4 twice. Remember, each input only needs to have 1 output, but that output could totally be the same. Just like in this rule, where everything became 7, it's okay if you have the same output a couple of times. What makes things tricky is, what if we have something like this? -2 gives us 5. Why does that not sit right? Well, if you said it's because -2 is already giving us 4, you're correct. This is not a function because -2 cannot output both 4 and 5. It's totally okay that -2 gives us 4 and 1 gives us 4. That just means that these are 2 different ingredients that give us the same product. What cannot happen is, if we plug in the same ingredient, we get different outputs. Then our machine is broken. One way that you can help detect if something is a function or not is to just find if there are any inputs that repeat. In this case, notice how -2 was repeating. If that -2 gave us the same output both times, we don't need to worry about it. It would be exactly like the example we did down here, where 0 gave us 3 in both cases. That's totally fine. But if they give you different outputs, then you'll know it's not a function. So always try to see if there are 2 of the exact same inputs. Let's try this one as well. Let's use that trick to help us out. Here, it says that 0 turns into 3. It says that 1 turns into 1. 2 turns into 1. 3 turns into 0. Well, we didn't have any repeats here. Each input gave us exactly 1 output. So we say yes. Each input produced only 1 output. That's how you can tell if something is a function or not. You might have noticed something already. And if you haven't, no worries. But here's the idea. We can't just call everything inputs and outputs all the time. I mean, it's a mouthful and it's a mess to write down. There's got to be some way of shortening it. You may be familiar with the way we shorten it based on how we organize them in pairs. Our inputs are what we are going to call x. Every time there's an input, we call the input x. Every time there's an output, we call the outputs y. So if I told you, for instance, I'm going to turn back to our notes page for this. If I told you that x equals 5 and y equals 7, that's the same as me telling you that the input is x and the output is y. That's why when we write things out in ordered pairs, it's in the form x comma y. We always write them with the input first and the output afterwards. Make sense? All right. The next thing I want to talk about is if we have a situation like a graph. So let's take a look at this example right here. Ignore the fact that it tells us it's a function. Just open up your mind for a second. Each of these dots would represent some sort of coordinate pair. In other words, we could write out this first dot as being maybe 1, 1, and this next one is 2, 2, 3, 3. And we could keep going, writing out all of those points. But that would be a little bit of a pain, and it gets harder when you have lines and curves. The way you can tell if a graph represents a function or not is something called the vertical line test. Let me give you a brief example. Let's say we have this graph that we're looking at, and we want to decide if it's a function or not. Well, we could totally write out all the points here. We would have 1, 1, 2, 4, 3, 2, and 4, 3. I knew I did something wrong there. Let's say we have all of these. Well, then we would have a function. Nothing really repeats, so we're fine. Let's say, though, that we put another point in right around here. This would be at x equals 1, y equals 3, so we would write it as 1, 3. Well, now we have two inputs that say the number 1. We have 1 here and 1 here. Because this is the list of all of our inputs, oops, I think I mixed up my colors briefly. Wait, no, I absolutely got that right. I apologize. Because these are our inputs and these are our outputs, we ask ourselves, what doesn't make sense? 1 is an input twice. We said that breaks our rule of being a function. But look at how it's represented on the graph. These are two dots that are on top of each other. That's why we have this thing called the vertical line test. The vertical line test is this. If you can draw a line through each part of your graph, and the line passes through only one dot at a time, it's a function. But if one line can pass through two dots, like we see here, it is no longer a function. So the reason why in our notes, this, for instance, on page 62 would be a function is because, well, you can see, if we were to draw a line through all of them, you can imagine the other lines, each line would pass through only one dot. So it works. What about this one? We don't have any dots. Well, the rule is still the same. Your line should only pass through the graph once. If it hits the line twice, then it is no longer a function. And as a reminder, this only works with the vertical lines. That's why it's called the vertical line test. So it's up and down. Let's try some of these out. I want you to take a second and determine whether or not 3 or 4 represent functions. Pause the video if you want to try this on your own. What do we think? We should have seen that this one was a no. Well, why? I can draw a line through this dot here just fine. I can draw a line through this dot here just fine. Uh-oh. When I draw this line, it passes through 2 dots. So this is not a function. Here, you could physically draw out every single line, but it would take you a million years. You just got to ask yourself, if I can imagine vertical lines, will any of these vertical lines pass through the graph twice? The answer is no. No matter where I draw my lines, it'll never pass through the graph more than one time. This is a function. All right. Back on the vocabulary page on page 61, there's just one more main thing we want to talk about. We are going to be skipping independent and dependent variables because this is something that's talked about in biology. We don't want to cross over too much of that information, but if you know it, you know it. To finish off, we're going to talk about the domain and the range. You might have heard these words before, but this is basically what they mean. The domain of a function is the set of all possible inputs, which, as a reminder, our inputs are x. The range of a function is the set of all possible outputs. So we're going to call, whoops, I realized I was cutting you off there, all possible inputs and outputs. We're going to call those our y's. Here's the deal. We want to basically make a comprehensive list of all the possible inputs or outputs of a function. Here's how we write it out. To show our domain, we write out the letter D, a colon, and if we have a bunch of points, for instance, we have these numbers here, we would just list out all of the inputs. Well, one of the inputs is 1. You don't need to list it twice because it only appears, you don't need to list it twice because we already know that 1 is part of our domain. We don't need to say 1 is part of our domain and also 1 is part of our domain. We also cover 2, 3, and 4. Is there a dot where the input is 5? No. So our domain could be 1, 2, 3, and 4. When your data is a bunch of dots, you can represent it like this. However, that's not always the case. Let's take a look at our range. Again, the range is all of the possible outputs or y values we could have. Let's say for a second that we went back to one of the examples we looked at. Let's take a look at this function right here. What are all the y values we could have? Well, there's a lot of them. You see that we have a y value here at 4. We have a y value here at 3, 2, 1, 0. We have one at 3.5. We have one at 2.5. We've got so many y values that we can't write all of them out. So instead, we list how high up these points are using an inequality. To write it out as an inequality, we have to ask ourselves, what is the highest / lowest point? Do we have a highest point on this graph? Well, no. our graph has these arrows that tell us it'll go up forever. So we don't have a highest point. Our range will also then keep going up and up and up forever. But do we have a lowest? Yes. The lowest point of our graph is here, at x equals 0, y equals 0. To show the range in this case, we would write it out as an inequality. Because 0 is our lowest point, that's our end point. We write 0. From here, we want to compare it to y. Well, all of our y values were bigger than 0, right? We said that y could be 1, 2, 3, 4, a million. But we also said that y could equal 0 because our graph touched 0. This is how you could also represent the range. To finish off this lesson, let's try out just these last two practice problems, problems 5 and 6. We want to find the domain and range for both of these functions. Please pause the video and try these out for yourself. How did we do on the first one? In the first problem, the domain is 0, 1, 2, 3, 4, and 5. Because that's all the x values on the bottom that our points could be at. Here we have a point at 0, we have a point at 1, we have a point at 2, 3, 4, and 5. So we list them all out. We don't use an inequality because it can't be anything in between these numbers. Like we couldn't get 2.5. There's no dot at 2.5. When it's a bunch of dots, you write it out like this. Our range, though, is interesting. It's only 3 and 4. All of these dots are at y equals 3. All of these dots are at y equals 4. We want to represent all of these in order, from lowest to highest. So our range is 3 and 4. All right, again, if you haven't tried out number 6, please pause the video and try it for yourself. This one was a lot more challenging, but here's the basis of what we see. The domain is everything in between -3 and 3, right? There's a dot here, so that tells us that -3 is the furthest left it goes. You have a dot here at +3, so +3 is the furthest to the right it goes, and x can be anything in between here. Everywhere in between we see line. So we say that -3 is less than or equal to x, which is less than or equal to 3. We use a compound inequality. Our range, we would employ the same technique. The lowest point it is at 0. The highest point it's at is at 3. Everywhere in between 0 and 3, a line exists. So we say the range is between 0 and 3, which we write as 0 is less than or equal to y, which is less than or equal to 3. Thank you so much, everybody. This is the end of section 3.1. Try out the homework for yourself. Let me know how it goes. As always, have a fantastic day.